Okay, let's get started. So what we did last time was I introduced the Gaussian approximation. So what we did was we took a potential of a degree of freedom, which I call phi, and we asked ourselves the question, if it's at the minimum of the potential, which is the mean value, phi bar, then the probability distribution will just be a delta function evaluated at phi bar. But if it's fluctuating in this potential, so we can think of it as fluctuating around like this due to thermal fluctuations, it'll have a probability distribution, which will be like the blue curve at the bottom, some kind of broader distribution than a delta function. And we want to know what that is. And so what we did was we said, let's imagine we had 1 degree of freedom. So we write down the partition function as the integral over the degree of freedom, e to the minus beta h. And then what we did was we expanded the Hamiltonian about the maximum point where the integrand is maximized. So I call that point Q0. And then what we did was we expanded to second order, so we get a Gaussian integral to do. And after we've done that integral, we end up with Z being just the mean field value, which is just this first term over here, and then the square root of pi times 2 times the lambda squared, where lambda is the inverse of this Hessian matrix. And so when we work out the free energy then, which is just e to the minus beta f is Z, then we simply get there's an extra contribution, which is this term over here, that comes from the fluctuations. So that was the 1 degree of freedom. It's very simple. When we go to n degrees of freedom, it's a bit more complicated. So what you have to do is well, what you have to do is write it as an expansion over your degree of freedom, where now where did it go? There it is. Okay. Well, what you have to do is expand the Hamiltonian to second order. So you have a matrix d2h by dq alpha, dq beta, and then when you write down the eigenvalues of that matrix, the end result is that you get the variable that tells you the fluctuation contribution. This lambda over here now is related to the eigenvalues of this Hessian matrix, and so you end up with the formula, which is just the same as we had for the 1 degree of freedom case, but now we sum over all of those different modes. Okay, so that's a multi-dimensional version. And then one way to write this is we can note that if I look at the matrix M, this Hessian matrix as it's called, then the product of the eigenvalues is just the determinant of the matrix. And so we can write in terms of the determinant of the matrix, the free energy is just the mean field value evaluated at the saddle point, the point where the slope is 0, and then half kt times the logarithm of the determinant of the matrix. So that's what we did last time. So what we're going to do today is we're now going to work out the infinite dimensional version of this. So the infinite dimensional version of this will be calculated using exactly the same method. And then we're going to use it to compute the correlation function of the system. And once we compute the correlation function, we're going to be able to then compute correlations and susceptibilities and response functions. And that's what we want to get to, because we want to start looking at what is the response of systems to perturbations. So the first thing I want to do is explain what is the generalization. So when we have an infinite number of degrees of freedom, so we have our Landau free energy, which is written down here in yellow, we have to do an integral now over all possible functions, eta. And the way we're going to do it is we're going to say, let's suppose I've got the volume V. So then I can write the eta as in terms of its Fourier components, eta k. And now I've got a discrete set of Fourier components. And so my functional integral d eta, what that really means is just the product over the allowed k values of the d eta, and then the Landau free energy as a function of the Fourier components. So let's now do this computation. So we're going to now work with the fact that we have a Landau free energy, which is integral ddr. So I'm going to write it as a half grad eta squared plus f of eta. And my f of eta, I'm going to write, following what we did in the second week rather, as a half b eta to the fourth, like so. And what we know is that if I'm above Tc, so T is greater than Tc, which means T, our variable T, is greater than 0, little t is T minus Tc over Tc. And so then we know that the potential f of eta, so b is greater than 0, a is a constant, a is greater than 0. So so when t is positive, then this looks just like a a potential with one minimum. Like so. And so this is going to happen at eta equals 0. And so what we know then is that the expectation value of eta is equal to 0. And then we're going to expand about eta equals 0. So that's going to be what we do for t greater than Tc. For t less than Tc, we have a slightly different picture. We're going to be generalizing this to continuous symmetry systems later. So then now what we have is, in this case, the free energy looks like that, and our potential has now got a double well like that. And we know that the expectation value of eta is going to be plus or minus at over b square root, and then we're going to be looking at fluctuations about that. So if we look over here on the left, what our fluctuations look like are simply fluctuations in this potential well, like so. So here we've got a choice. We've got fluctuations either around this well, or we have fluctuations around this one over here. And so what we're going to have to do is we're going to have to make a choice which well we expand about, and then compute the Gaussian integration about that particular minima. So the strategy is going to be to choose our minima, choose one of the minima, which is in some sense breaking the symmetry. And then compute the Gaussian fluctuations. Okay, so let's, I'm going to do this calculation. I think what I'm going to probably do is, I just want to check, I think I'm just going to do it for t greater than Tc, and I'm going to let you do it for t less than Tc in homework. So it's the same calculation, but there's going to be just a very slight difference, but it will be a great way for you to check it. So the first thing we're going to do is, let's start off by looking at t greater than Tc. And so the first thing I need to do is write down what is the Landau free energy. So we're going to expand the Fourier series about eta equals 0. So we're going to simply substitute in, and what we're going to get is the following. So we're going to be summing over two k values, k and k prime. Why? Because what we're going to be doing is we're going to take eta of r, write it as a Fourier series in k, and then we've got everything here is going to be quadratic. So there's two eta of r's. So therefore there's going to be two different k's. We remember that we have dummy variables, so we keep track of those dummy variables. So then we're going to write this as integral d dr over v squared. And then our Landau free energy is going to look like this. It's going to look like 1/2 gamma minus k dotted with k prime plus at times eta of k prime, and then e to the I k plus k prime dotted with r. So all I've done is I've substituted in the definitions of Fourier transform that I wrote down last time, somewhere over here. So all we've done is substitute in the definitions up here at the top of the page. Eta of k is equal to that. So we've simply substituted back in eta of r is the reverse Fourier transform, and we've simply substituted that back in. Okay, so now let's we can do this integral. So the integral over r, we can the only place that r occurs. Let's just have a look where it is. So r occurs here. And then the only other place that r occurs is over here in the exponential. So when we do that integral over r, what are we going to get? We're not going to get a Dirac delta. We're going to get a Kronecker delta. Okay. So if you look back in our notes, last time we defined the different deltas. So what we're going to get when we do that is we're going to now get 1 over v, then the sum over k and k prime, and then 1/2 gamma, and then minus k dotted with k prime plus at eta k prime, and then after doing that integral, we're going to get delta of k plus k prime and 0, and that comes in here in this summation. So doing the integral over r gives you a delta function of k plus k prime. This is, sometimes we call this a momentum conserving delta function, because that's the way we can interpret it. And the other thing that I want to point out before I go on is that we know that eta of r is a real variable. And so because it's a real variable, then if I take its Fourier transform, that means that eta of k star is equal to eta of minus k. So if I say eta is equal to real, that means that eta equals its complex conjugate. So then if I put that into the Fourier transform, it means that the Fourier components of k and minus k are not independent, they're just their complex conjugate. And so that's going to be a constraint that we're going to need when we do the integration. So now we can say that once we have that, once I do the delta function, then k is equal to minus k prime. So now what I end up with is 1 over v sum over k. Now there's only one k value left, 1/2 And then I've got eta of k, eta of minus k, that is eta of k times its complex conjugate. So that's absolute value of eta k squared times 2at plus gamma k squared. And so that's the form for our Landau free energy after I've done all those things. So then if I want to compute the functional integral for the partition function, so that's this thing, this I can write as the functional integral is now just going to be an integral over the Fourier components d eta of k, and then e to the minus beta times 2at plus gamma k squared, and then eta k squared, and then that's over 2v. Okay, now one thing I want to point out, another comment, is that when I write down eta of k squared like so, so that means it's the real part of eta of k squared plus the imaginary part of eta of k squared. So that's what we mean by that. And then the second thing is, if I think about what is d eta k, so d eta k, this is like if I have a variable z is equal to x plus iy, then the absolute value of z is x squared plus y squared. But when I write down dz, what I actually mean is dx dy. In other words, the real part of eta times d imaginary part. So when I write down these integrals, I'm actually integrating over twice as many degrees of freedom as you might think, because I've got the real part and the imaginary part. Okay, so that's the first thing. The second thing is, if I look at this integral, what it basically looks like is the integral, each of these integrals factorizes. So this factorizes. So I can say that z is equal to now the product over k. I can take the product outside, and then I've got d eta of k e to the minus beta times some number, which I'm writing as 2at plus gamma k squared, eta k squared divided by 2v. So now what's different is this product is now outside, and inside here is just one integral. So the way you should read this is you tell me what value of k I'm using. Okay, it's 17 or whatever it is. That's the value that labels the eta variable. And then that value of k is the one that we put in the exponential, and that's the one that we use to label the eta variable. And so this is just a Gaussian integral in one variable, but it's actually in two variables. So this thing is of the form, the integral from minus infinity to infinity, dx dy, e to the minus some number a times x squared plus y squared. So that's what it looks like, where a is this object that you can read off in here. So now I just have to do that integral, and we know that this integral is equal to, well, it would be root pi over a if it was just one integral, but I've got a product of them. So this is actually equal to pi over a, because there's two variables. And so then what I end up with then is that the free energy is equal to the free energy when the system is at eta equals 0 minus 1/2 kBt. And now I've got to sum over all the k modes. And then I've got the logarithm of 2 pi v kBt over 2at plus gamma k squared. So that's just taking that formula and then summing over all the k modes and just plugging into the result that we obtained last time. So this is the analog of what I have here over here on the left-hand side of the screen, over here on this equation, where we had, look on the left side of the screen over here, where I'm writing. So this is the analog of that, but now it is summed over k modes. Now, which k modes are they? Well, remember that to construct this Landau free energy, we had a coarse-grained description of the system. So this is over wave numbers k, which are less than my coarse graining scale lambda. So it's not over all k; it's cut off at the ultraviolet. Okay, so that is a final result for this, and I want to make one other comment about it. What we have on the previous page over here, you can see that eta of k and eta of minus k are not independent. So when we do the sum over k, this sum over k modes, whose magnitude is less than lambda, that sum is only over half of space, only over half of k space. Because if I sum over all of k space, I'm double counting. The modes of eta of k and the modes with eta of minus k are the same. They're just related by a complex conjugate. So they're not independent. So when I do this sum, I have to sum only over a half space. Say kz is greater than 0. And the reason for that is because eta of k and eta of minus k are not independent. So I don't want to double count, I only want to count each mode once. Okay, so that's how we do the free energy. And even though it's taken us a while to get this result, actually, that's not the most important thing that we want to compute. The thing that we actually want to compute are correlation functions. So now I'm going to talk about correlation functions. Before I do that, let me just quickly look ahead. I just want to make sure that I said all the points that I wanted to say. Yep. Okay. Okay, so what are correlation functions? What question do they answer? So they tell me the following thing. If I know the value of the order parameter at one point in space, what can I infer about the order parameter at a different point in space? So the question is, if I know eta of r, what do I know about eta at a different point, like that? And what do we expect? Well, we expect the answer is going to depend on how far away they are. So if I've got two spin variables or order parameter variables very close to each other, they're going to be highly correlated. If one is up, the other is going to be down, and so on and so forth. If they're 100 miles apart, they're probably not going to know what each other is doing. So what we expect is that this depends on distance. And the question is exactly what? So the way I'm going to quantify this is we're going to construct the two-point correlation function. So I'm going to write it down like so. So g of r and r prime. I'm going to define it in the following way. I take eta at the point r, and I subtract the average value of eta at that point r. And then I compute eta at r prime minus the average value of eta at r prime. And then I take the expectation value of that. So let's unpack what this means, because sometimes people get confused about what it means, or they don't think very carefully about it. So this thing over here, this thing is the fluctuation at r of eta of r about its mean value. And we expect that our system is translationally invariant. So if it's translationally invariant, then we expect that this will only depend on the difference between these 2 points. Like so. And therefore, and we also expect that eta of r is the same as eta of r prime for any r prime. So in other words, it doesn't depend on space. So that's the first thing. So this thing here is a fluctuation. And so what we're measuring with the g of r, so I can think of this as being the expectation value in thermal equilibrium of the fluctuation at r and the fluctuation at r prime. So remember, when people talk about correlation functions, they forget that what we're talking about is not just the correlations of what? We're talking about the correlations of the fluctuations. So G is called the correlation function of fluctuations. It's not the correlation function of the order parameter, it's the correlation function of the fluctuations. We can define a correlation function of the order parameter itself, but it's the fluctuations that actually matter. So let's ask then what is let's ask then what we expect G of R to look like. So what we're going to look at is we're going to average over the system, and we're going to look at the fluctuation over here and the fluctuation over here. If they are different, if R and R prime are far apart and they're different, then when I average those out over the whole system, they're going to add to 0. If there's going to be regions where R and R prime are strongly correlated, so wherever the fluctuation over here goes up, the fluctuation over here goes up, then I'm going to get a positive number. If over here the fluctuation goes down and the fluctuation goes down in the same way, I'm also going to get a positive number. So what's going to happen is that the dominant contribution to G will come from regions where delta eta of R is roughly the same as delta eta of R prime. And so that's what this thing measures. And in regions where they're uncorrelated, will make no contribution. So let's suppose that they're uncorrelated. So let's have a look at what is the expectation value of delta eta of R. So this is then the expectation value of eta of R minus the expectation value of the expectation value of eta of r. So let's suppose the expectation value of eta of r is equal to 3. What is the expectation value of 3? It's 3. So then this thing is then the expectation value of eta of r minus the expectation value of eta of r, and that is equal to 0. So if I have two regions, if delta eta of r and delta eta of r prime are uncorrelated, then G is going to be the expectation value of delta eta of r, expectation value delta eta of r prime, and then it's going to equal 0. So G of r truly measures how correlated the system is. Now, the question that we want to calculate is what is the thermal expectation value of G? So the question is how to calculate. The answer is that we're going to use the equipartition theorem. Okay, so I asked you as a homework exercise to remind yourself what the equipartition theorem is. So what is it? Teacher. Okay, that each degree of freedom has the same amount of energy. Is that what you said? Okay. Anybody would like to make it a bit more precise? Is it true for any Hamiltonian? Every degree of freedom? Is what?
If you have a Hamiltonian, if you have a system with some degrees of freedom, then you have the Hamiltonian, which is quadratic, in those degrees of freedom. Each quadratic term, you take the expectation value of that energy contribution. It's going to have the same expectation value of the energy. So that's going to be half kb.
Okay, so I think you said it right. So first of all, it says that if I have a classical Hamiltonian, it is quadratic in the degrees of freedom. Then each degree of each term in the Hamiltonian has an average value of 1/2 kBt. Okay, so your Hamiltonian has to look something like this. H equals a q1 squared plus b q2 squared plus c q3 squared, whatever. And then you should be able to prove the expectation of q1 squared equals the expectation of b q2 squared equals the expectation of c q3 squared, and that is 1/2 kBt. Okay, and you should be able to prove that. Okay, so it's just a Gaussian integral. So if you don't know it, check it. Okay, all right, so we have, why do we care about this? Well, we have a Landau free energy that is a quadratic. So our L, which I'll sometimes call an effective Hamiltonian, is 1/2 sum over k modes 2 at plus gamma k squared over v times eta k squared. That's it. That's our Hamiltonian. So this is quadratic. So I know straight away that every term has expectation value equal to a half kBt. So what that means is if I look at the, if I compute that, so put an average around each of these terms, so each term is of the form, I've got 2at plus gamma k squared over v times eta k squared. That has got to equal 1/2 kBt. And I think I need a half in here to make this correct. But you can double check that. Okay, so that's the result. Is this correct?
We need to consider the negative value.
Well, remember that I've just chosen a value k. Remember, k is just a label. Space is just a label. In reciprocal space is just a label. So you tell me what k you want. 17. Okay, k is 17. I claim that this is true. Is it correct? Okay. Yes. Yes. No. Yes. 3 yeses, 1 no, 1 not quite sure. Cindy. Okay, so Chan is right. Why did you say no?
I'm not sure, but I think like 1/2 is
Okay, well, so let's see. Your logic is that Nigel usually makes mistakes of factors of a half, so there's probably a mistake. So, and also I wouldn't be asking if it was correct, probably, right? So there is a factor here which is 2. Why? Complex. So this thing is equal to the real part of eta k squared plus the imaginary part. So in the end, what we end up with is the formula. Is this kBTV over 2at plus gamma k squared. Now, I want to make sure, I want to remember that there's a warning. So last time I taught this, I realized that there is a typo in my book around the area where this part is done. Okay, and I don't remember which part where the typo is, but I know there's a typo there. So if you go through and work this out for yourselves, you might find that there's a typo, and if you find one, it probably means that you're correct. There is an erratum page of typos in my book online. So I don't remember if I corrected it or not. So you're going to figure it out. All right. So, but this is pretty close. This is either correct or correct up to a factor of a half. Right. Okay. So this is what we've computed here is the order correlation function of e to k. We haven't computed the correlation function yet. So now I want to use this to compute the correlation function. So the trick is to do a Fourier transform. So I claim that if I take eta of k squared, then this thing is equal to the integral d x1 d x2 e to the I k dotted with x1 minus x2 times eta of x1 eta of x2. And that's my my claim. Where did this minus sign come from? The minus sign over here. This minus sign. Where did that come from? That came from the fact that eta of k squared is eta of k eta minus k. So that's how I got that. Now this thing over here is I claim that this thing is equal to v times g hat of k, where the integral ddx1 ddx2 e to the I k dot x1 minus x2 so this thing is equal to this. So how do I do this integral? Well, what I can do is this. I'm going to pretend that this integral over dx doesn't exist. So I'm going to cancel that out. So this, I'm just going to set x1 equal to some fixed value. Let's say it's the origin, like that. Then I go ahead and do this integral, like so. And that integral is just the same thing as the integral ddx2 e to the I k dot x2 g of x2. And then that thing is equal to, by definition, the Fourier transform of the 2-point correlation function. So that's that integral, and the x1 didn't come into this. So now when I do the integral over x1, so now restore this integral into here. So when I put this integral back, that's just going to give me a factor of v. So what that means then is I can put this all together. And so now I've got that the 2-point correlation function is equal to kbt over 2at plus gamma k squared. So the factor of the v has gone. And I'm going to write this in the following form as kbt over gamma times 1 over k squared plus a variable, which I'm going to call psi to the minus 2. And this psi to the minus 2 is equal to 2at, and therefore psi greater than, as a function of t, is equal to 2at to the minus 1/2. Okay, so let's unpack that. So what did I do here? I took eta of k squared, So I computed over here where I have the exclamation mark on the left, I computed the expectation value of the absolute value of e to k squared. And then I showed you that that absolute value of e to k squared is in fact the Fourier transform of the 2-point correlation function times v. So therefore I can then say that the 2-point correlation function is just kbt over 2at plus gamma k squared. So I started off by computing using the equipartition theorem to compute the autocorrelation function of e to k, and then I showed you that this thing is just the Fourier transform over here of the 2-point correlation function. That's the first thing. The second thing that I did was then I used that formula to write it in this particular way. So let's unpack this. So this is just, this is a factor of kbt over gamma. So that's just what it is. That's what we calculated. And then I've written this part as 1 over k squared plus something. K has dimensions of inverse length. So whatever this thing is here, it has dimensions of inverse length squared. And so I'm going to call that inverse length psi. And I'm calling it psi greater than. Psi greater than is in fact the correlation length for t greater than 0. So the greater than symbol is because of this symbol over here. There's a gamma. There is a gamma. There is. There's a typo there. I think that's correct. Yeah. Anyway, don't try to check the algebra in real time. All right, so that's the first thing. So what I've shown you is that we've discovered a length scale, and not only have we discovered a length scale, but this length scale diverges as t goes to 0. So this length scale as little t goes to 0, and we're above tc, so t is going to 0 from above. So this length scale. You might wonder, well, what is this length scale? Well, let's what is the physical meaning of this? So let's calculate what a g of r looks like in real space. So I'm going to do it in 3 dimensions. So now what we have to do is we have to compute the Fourier transform of 1 over k squared plus psi to the minus 2. And this is just equal to the Yukawa function, 1 over r e to the minus r over psi. And so then what we've computed is that g of r in real space is equal to kbt over gamma times e to the minus r over psi greater than divided by r. And so what that tells you is that now we've just proved that correlations decay in space exponentially. And that's why we can interpret psi as a correlation length. So remember at the beginning, we said we're looking at correlations or fluctuations. If they're very close by, we would not be surprised if they're highly correlated. If they're very far apart, 1,000,000 miles apart, we'd expect them to be uncorrelated. And we've just proven that the correlation decays exponentially. So it fulfills exactly our intuition. Okay, so that's what we just computed. So there's one other comment that I want to make. So let's compute for ourselves eta of r prime. So let's just do that. So the way we're going to do it now is we're going to use our result for the correlation function. So we're going to write this as 1 over v squared, sum over k and k prime, e to the I k dot r plus k prime dotted with r prime, and then eta of k prime. Okay, so that's the thing that we've just calculated. And what this is, just putting together the result from above, is just 1 over v, the sum over k of kbt over 2at plus gamma k squared, and then e to the I k dot r minus r prime. So what I've just shown you is that this thing over here is g of r and r prime, and this thing over here is clearly a function of r minus r prime. And so we've shown that this thing is translationally invariant. Okay, so that's true for t greater than tc. We've now computed the correlations for t greater than tc. So homework is to do the same thing for t less than tc. And you follow the algebra, but the result is going to be slightly different, and it's different in a slightly interesting way. Okay, so now I want to talk about the next topic. I want to talk about susceptibility. And response functions. So we've just learned how to, do you have a quick question?
Yeah, why does this diverge for small r?
Why does it diverge for small
Yeah.
r? This result is
Oh, is it because we were only supposed to integrate over, like we integrated over all k, but the ones with extremely short wavelength should have been excluded, so like a regime.
right. So what actually happens if you compute this exactly? Well, so the usual result is that that at long distances it will decay exponentially. At short distances, actually, this result isn't quite correct. Yeah, I want to give you a fuller response to that, but I want to move on. So here's what I'm going to do. I will give you an explanation about that subtle point in Teams after the lecture. Okay. There is an interesting point here, but I don't want to get too distracted for that. But you can see also that there's something funny that happens anyway, because the first correction, you can see that the r's cancel out when you do if you expand your exponential. So there is something interesting here, but I don't want to go too far away from that. All right, here's what I want to do next. I want to look at the susceptibility. So up to now, what we've looked at is that we have our Landau free energy. Okay, I'm going to make myself a note here. So just a comment. Short distance behavior. So I didn't forget that. All right. So what we've done so far is we've looked at this Landau free energy, but we haven't put in any external field. So now I want to ask what happens when we include an external field, and that external field could in general be space dependent, and so it would come in like this. And I want to ask what happens when we have such an external field. Okay, so the question is the following. So in equilibrium, so we have that the expectation value of eta is a constant in space. And when h is equal to 0, we have eta is equal to 0, or if you're below Tc, minus AT over B, square rooted like that. So then the question is, how does expectation value of eta change when you turn on H? So that's the question. We're going to ask, how does the system respond to an external field? And so the way we do that is we say, well, what you've asked me to compute is the isothermal susceptibility, which I can write down as this. I take the expectation value of eta, and I look at what happens when I switch on H. So this is called isothermal susceptibility. And let's compute that. So we're now going to compute this when H is non-zero. So when H is non-zero, when I compute dL by d eta and set that equal to 0, then what I'm going to get is actually a different equation than the one I've got before. I'm going to get 2AT eta plus 2B eta cubed is equal to H. And so therefore, if I compute now, so that's dL by d eta. Now I compute d by dH of that. So I've said it poorly. This equation tells me what is the value, the equilibrium value of eta. And then now I want to work out how this equilibrium value of eta changes with H. So I first of all have two steps. One, differentiate and make the Landau free energy stationary, and then compute the derivative. So if I compute the derivative, if I differentiate with respect to H, so what I get, so I want to compute this. So what I can do is take this equation, compute d by dH, and so what that's going to give me is that chi is equal to 1 over 2 AT plus 6B expectation value of eta squared. And here I've made the mean field assumption that eta is replaced by its average value. Okay, so if I've got T greater than Tc, then what that means is the expectation value of eta is itself 0, and so that means that chi t is 1 over 2 AT. So what we've learned is that if I look at the susceptibility, how sensitive the system is to, I apply an external magnetic field and I ask, how does the order parameter change? What I've just shown you is that if I'm very, very close to TC, actually the susceptibility actually diverges as T goes to 0. So as T goes to 0 from above, the isothermal susceptibility diverges to infinity, and this divergence is one of the critical phenomena that we talked about last quarter. Okay, so that's great, but it's not what we want to understand. We want to understand. Now we want to understand how does this have to do anything with spatial correlations? So let's think about the intuition that we have. So our intuition is this: what the correlations tell you they tell you how eta of r prime depends on eta of r. So you might say, well, if I apply an external field H at the point R, then what that's going to do is it will change eta of R locally and through the correlation function which reflects the interactions in the system. That will affect eta at a point r prime where r prime is not equal to r. So I take the system, I apply an external field just over here, and because things are correlated due to the interactions, there is going to be an effect of it a distance away. So we want to figure out what is that long distance, what is that long distance interaction. So this argument then should tell you that we expect there to be a connection between the correlations and susceptibility and response. So I'm going to show you that that's exactly true, and we're going to see it in a very simple way. So let's illustrate that. We're going to illustrate it with a uniform external field, so a spatially uniform H. And what I'm going to consider now is we've computed what chi is. So we're going to do this for t greater than 0. So what do we know? So in this particular case, we know that chi is 1 over 2 at. So now what I want to do is I'm going to consider the following connection. Let's consider the integral over space of d dr, some dummy variable, the 2-point correlation function as a function of r. So what is this? Well, this is then the integral over space of eta at r, eta at some arbitrary point, let's call it the origin, like so. And then this is then 1 over v, the sum over k, kbt over 2 at plus gamma k squared times the integral d dr of e to the I k dot r. And this then is 1 over v sum over k kbt over 2at plus gamma k squared. And then this thing on the left is just v times delta k0. So the v's cancel out. And then the k is equal to 0. So I just set k equal to 0 in here. And then what I end up with is this thing is equal to kbt over 2at. And this you can see is kbt times the isothermal susceptibility. So I've just showed you that that the integral of the correlation function over space is actually equal to the susceptibility. And I just showed it for you for t greater than tc, and you can prove it more generally than I've done here. And that's explained in my book. So this result has a name. So if you want to look it up in my book, this is called the static susceptibility sum rule. And it is, here I did it by working backwards from the answer, but you can prove it more generally, and that's explained in my book. And so you can look at that if you haven't seen it before. Okay, so now what I want to do is I want to apply this to our systems with continuous symmetry. Excuse me. So what we've done, it's been a bit of a slog. What we've done is we've learned how to compute correlations directly from our coarse grain description. Now I want to start looking at what happens when we have a system with a continuous symmetry, and we're going to be looking at the ON model. And what we're going to find is that the susceptibility and the Green's functions, the correlation functions, all behave very differently. Susceptibility and the correlations have a remarkable tensor structure. And from this, we're going to prove a theorem called Goldstone's theorem. And we're going to see the emergence of rigidity. So we've actually done all the hard work. And so the rest of this is a sort of downhill kind of calculation. So let's do it. We're going to generalize everything. Everything that we've done before, we're now going to generalize to the ON model. So here's the setup. We're going to apply an external field H. And that's going to be proportional to some unit vector. So H is equal to the magnitude H times n hat, but this is a unit vector in spin space, not real space. Okay. So we're going to now imagine what happens if I take a system with continuous symmetry. Now it is going to order, and it's going to order in some direction in space. So we're going to assume that the spins order parallel to some direction n hat. So I can write down my order parameter as m, I'm going to call it m alpha, and that's going to be the expectation value of S alpha. It's a function of space, and alpha is the component in spin space. So alpha goes from 1 to n, and this I'm going to write as m, a magnitude, times the unit vector n alpha. So this defines the magnitude of the ordering. So the labeling here, this is alpha goes from 1 up to n. And what I'm going to do is, without loss of generality, I'm going to assume that the ordering direction in spin space is 1, 0, 0, 0, like so, where there are n entries in this vector. Okay, so that's the setup. So our spins have ordered, and now we're going to look at what happens when I apply an external field. So I'm going to define two types of correlation function. So the first one is the longitudinal correlation function. And you'll see why it's called that. So I'm going to define it as G parallel of K. I'll try to remember to put a hat here to remind you it's a Fourier transform variable. And what I'm going to do is I'm going to look at the order correlation function of the one component of the order parameter as a function of space S of K. So I'm going to write it down like that. So this is just like the order parameter, order correlation function that we've written down for the scalar system, but now this is just for the component in which the system is ordering in the particular direction. So that we're going to call the longitudinal one. And then I'm going to define a transverse one. And the transverse one, I'm going to define it in a very sneaky way. I'm going to define it in such a way that it has a particular tensor structure, which will then turn out to be very convenient in a little while. So I'm going to define it like this. I'm going to define a function, g hat, that depends on k. And then I'm going to write it as v delta alpha beta, then delta k plus k prime and 0. And I'm going to define this thing is equal to the expectation value of S alpha of k, S beta of k prime. And here alpha and beta are components that are not 1, so they're greater than or equal to 2. So here's the system. Here's my system. I've got my spins. They're all more or less pointing in this direction over here. There's n-1 directions that are perpendicular to this direction. Okay, there's an ON model. It's pointing in one direction. All the other n-1 components are orthogonal. I look then at the correlations of those n-2 components that are not in the direction of ordering. So I choose which component, S alpha, S beta, alpha equals 16, beta equals 194. I look at the correlation of those, and I'm also going to do it by taking their Fourier transform and looking at the components k and k prime. And then the answer is going to be, I'm going to get some function, but you know that momentum is going to be conserved because our system is translationally invariant. So you can predict that the result is going to be that k is going to be 0, and thus k and k prime conserve momentum. In other words, that they're equal and opposite. And you can also expect that because our system has ON symmetry, that the orthogonal components will be independent. And so these factors of delta alpha beta and delta k plus k prime are going to emerge from the calculation. Okay, so that's the things that we want to compute. And then, so I've got longitudinal and transverse correlation functions. So then I'm also going to compute longitudinal susceptibility, which I'll call chi parallel, and transverse susceptibility, which I'm going to call chi perpendicular. And you might imagine, by analogy with what we did over here, where I computed, what we did on this side is I computed over here, this is the k equals 0 component of g hat of k. Why? Because look over here, integral d dr of g of r. That's like taking the Fourier transform of g of r, integral g of r e to the I k dot r, and setting k equal to 0. So what I just showed you was that the k equals 0 component of g hat of k is equal to the susceptibility up to some factor of kt. So you might expect that these things over here are also going to be related to the perpendicular components. And this, the 0, that is, the variable that is 0 here is k equals 0. So we're going to expect something like this. Okay. All right. So that's what we expect. And we expect this because the static susceptibility sum rule relates chi t times kbt to g hat of k equals 0. Okay, so that's the setup. So what I'm going to do on Thursday is I'm going to show you now that because the free energy of the system, the Hamiltonian of the system has ON symmetry, we're going to see that this gives us a very intricate tensor structure of the correlation functions. What I'm going to show you is that the system, longitudinal correlations decay exponentially, just like I showed you for the scalar case, for discrete symmetry. But we're going to see that the transverse correlations decay as a power law. And you might say, oh, they decay as a power law. Well, sure, because it's a critical phenomenon. We already saw that you can get power law decay of correlations and so on near a critical point. But the point is that this is not near the critical point. This is far away from the critical point, well below TC. Well in the ordered phase, you still have power law transverse correlations. Okay, even if which have nothing to do with criticality, they have to do with the symmetry of the system. And that result is going to end up being what's called a Goldstone's theorem, but it's related to that. And just as a teaser, if you look, let's go back here and look at the form for the correlation function that we derived. So go and look at this. Okay, 1 over k squared plus xi to the minus 2. How many of you have done some elementary quantum field theory? Oh, okay, only 1 or 2. Okay, it's super elementary. In quantum field theory, you have massive particles. And if you compute what's called the Feynman propagator, in quantum field theory, when you compute the propagator, which is basically the correlation function, you get a formula that looks like this: 1 over k squared plus m squared. Some of you seen that before, where m is the mass of the particles. So you can see here that the mass of the particle in quantum field theory is played by the inverse correlation length of the statistical field theory. So in statistical mechanics, you have correlation lengths. In quantum field theory, you have particle masses. So you can see then that if we have a power law decay of correlations, which means that psi is infinity, so that psi to the minus 2 has gone away, so we just have 1 over k squared. In terms of in terms of the propagator in quantum field theory, that means that the mass is equal to 0. So this phenomenon that I'm just telling you about is the analog of how you can get massive bosons in a quantum field theory. And that comes from, we're about to see that in the next lecture. Okay, so all of this is now going to start to come together. Okay, so I'm going to end there and let me turn off the recording.